when we look up at the night sky, it often feels quiet and simple. A few bright stars appear scattered across the darkness, each one shining gently from far away. For most of human history, that was all people could see. The stars looked like distant points of light, almost like small holes in the sky. But the reality is very different. Those points of light are not small at all. Each one is an enormous star, many of them larger than our sun. And together, these stars belong to a vast structure that surrounds us. That structure is called the Milky Way galaxy. Our sun is just one member of this enormous system. It is one star among hundreds of billions of others. Many of those stars have their own planets, their own systems, and their own stories unfolding across space. The Milky Way stretches across the universe in a wide spiral shape made of stars, clouds of gas, and drifting dust. When scientists study it, they find that it is not a small neighborhood of stars. Instead, it is a gigantic cosmic city filled with stellar systems spread across an almost unimaginable distance. And our solar system sits quietly inside it. We are not near the center of the Milky Way. We are also not close to its outer edge. Instead, our sun lives in the middle region of the galaxy, orbiting slowly along with billions of other stars. All of these stars are moving together around the galaxy's center, each following its own long path through space. From our position here on Earth, we cannot easily see the full shape of the Milky Way. We are inside it, surrounded by its stars. This makes it difficult to step back and look at the whole structure at once. But we can still ask an interesting question. What would it take to travel across the Milky Way? Imagine beginning your journey near one outer region of the galaxy. You set a course toward the opposite side, heading through billions of stars and vast clouds of gas. The trip would take you past star clusters, through spiral arms, and eventually across the crowded central regions where stars are packed much closer together. Then you would continue onward, leaving the center behind and traveling out toward the distant outer edge on the far side of the galaxy. Even imagining such a journey begins to stretch our understanding of distance. The space between stars is enormous. Even the nearest stars to our sun are separated by distances so large that human spacecraft would need thousands of years to reach them. But the Milky Way is not just a collection of a few nearby stars. It contains hundreds of billions of them spread across a huge region of space. Traveling from one edge of this galaxy to the other would mean crossing one of the largest structures we can observe directly from Earth. For many centuries, people did not realize that the Milky Way was a galaxy at all. Ancient observers simply saw a glowing band stretching across the night sky. This pale ribbon of light was visible on very dark nights, far away from city lights. Because it looked like spilled milk across the sky, many cultures gave it names related to milk or mist. The term Milky Way itself comes from an old Latin phrase meaning Milky Road. Today, we know that this glowing band is made from the combined light of billions of distant stars. When we look along the flat disk of our galaxy, all of those stars blend together into the soft glowing band that crosses the sky. For astronomers, understanding this structure became an important challenge. Scientists wanted to know how the galaxy was shaped, how far it extended, and where our own solar system fit inside it. But measuring something as large as the Milky Way is not simple. Unlike distant galaxies that we can photograph from the outside, we are located within the Milky Way itself. Trying to measure its full size is a bit like trying to measure the size of a forest while standing among the trees. You can see the nearby trees clearly, but understanding the full shape of the forest takes careful observation and patience. Over the past century, astronomers have slowly built a clearer picture of the galaxy we live in. Using telescopes, careful measurements, and new technologies, they have begun to map the stars around us and estimate how far the Milky Way extends across space. And what they discovered revealed something remarkable. Our galaxy is far larger than anything humans experience in everyday life. To understand just how large it truly is, we first need to explore the special way astronomers measure distance across the universe. To understand the true size of our galaxy, we first need to talk about how distance is measured in space. On Earth, we usually measure distance using familiar units like meters, kilometers, or miles. These measurements work well for everyday travel. We might measure the distance between two cities in kilometers or the length of a road in miles. But when astronomers look out into space, these ordinary measurements quickly become difficult to use. The distances between stars are so large that writing them in kilometers would create numbers with many zeros. Even the nearest stars are separated from our Sun by trillions of kilometers. When scientists began studying these enormous distances, they realized that a different system would be much easier to use. Instead of measuring space using distance alone, astronomers often measure it using time. More specifically, they measure how long it takes for light to travel from one place to another. Light is the fastest thing we know of in the universe. In the empty vacuum of space, light travels at a speed of about 300,000 kilometers every second. This number is difficult to imagine, so it helps to compare it to something more familiar. At that speed, light could travel around the entire Earth about 7 times in a single second. In the time it takes you to blink your eyes, light could circle our planet several times. If we stretch that time out a little longer, the distances become even more impressive. In just 1 minute, light travels about 18 million kilometers. In 1 hour, light travels over 1 billion kilometers. These numbers already seem enormous, yet they still describe only short distances when we begin talking about the scale of the universe. Astronomers therefore often take the next step and measure how far light travels in an entire year. When light moves continuously for a full year at its incredible speed, it covers a distance of about 9.46 trillion kilometers. Scientists call this distance 1 light year. Despite its name, a light year is not a measure of time. It is a measure of distance. It simply tells us how far light can travel during 1 year. This unit turns out to be extremely useful when describing the distances between stars. For example, the nearest star system to our Sun is called Alpha Centauri. Even though it is the closest star system to us, it is still about 4.3 light years away. That means the light we see from Alpha Centauri tonight actually left that star more than 4 years ago. Many other stars are even farther away. Some stars that we can see in the night sky are hundreds of light years from Earth. Their light began traveling toward us centuries ago, long before modern technology existed. When astronomers observe distant stars or galaxies, they are often looking at light that has been traveling through space for very long periods of time. In this sense, looking deeper into space also means looking further back in time. The concept of the light year helps make these vast distances easier to understand. Instead of writing distances with trillions or quadrillions of kilometers, astronomers can simply describe how long light would need to travel to cross that distance. This gives a clearer sense of the scale involved. It also reminds us that space is not just about distance, but also about time. Light carries information from distant places across the universe. The farther away something is, the longer its light must travel to reach us. When we observe distant stars, we are seeing them as they existed years ago. When we observe distant galaxies, we may be seeing them as they existed millions or even billions of years in the past. This idea becomes especially important when we begin talking about the size of our own galaxy. The Milky Way is filled with stars that are separated by enormous distances. Measuring those distances requires units that match the scale of the galaxy itself. Light years allow astronomers to describe these distances in a way that is easier to understand. Once we start using light years as our ruler, we can begin to explore how far away different parts of the Milky Way actually are, and how vast our galaxy may truly be. When we measure distances here on Earth, we usually think about space in terms of length. A road might be 10 kilometers long. A city might be 50 kilometers away. These measurements are simple and familiar because the distances involved are relatively small. But space is not small. Even the nearest stars are separated by distances that are far beyond anything we experience in daily life. When scientists began trying to measure these distances, they quickly discovered that using kilometers or miles became difficult. The numbers grew extremely large. For example, 1 light year, the distance light travels in a single year, is about 9.46 trillion kilometers. That number alone already contains 12 zeros. Writing distances between stars using kilometers would require enormous numbers that are hard to read and hard to compare. Astronomers needed a more practical way to describe such distances. The solution was to measure space using the time it takes light to travel from one place to another. Since light moves at a constant speed through empty space, scientists can use it as a kind of universal measuring stick. If we know how fast light travels, then we can measure how long it takes for light to move between 2 points. From that time, we can determine the distance. This is why astronomers often describe distances using light seconds, light minutes, light hours, and light years. These units make it easier to picture how far away something is. For example, the Moon is about 1.3 light seconds away from Earth. That means light leaving the Moon takes about 1 1/3 seconds to reach us. When astronauts visited the Moon during the Apollo missions, radio signals traveling at the speed of light took a little over a second to travel between Earth and the spacecraft. The Sun is much farther away. Light from the Sun takes about 8 minutes to reach Earth When you see sunlight shining on the ground, that light actually left the sun 8 minutes earlier. If the sun were to suddenly disappear, it would take 8 minutes before we would notice the change. These examples help show how time-based measurements can describe distance. Once we move beyond our solar system, the numbers grow even larger. The nearest star system to Earth, Alpha Centauri, is about 4.3 light-years away. This means the light from that star takes more than 4 years to reach us. Many stars in our galaxy are hundreds or even thousands of light-years away. Their light has been traveling through space for centuries or millennia before finally reaching Earth. This leads to an interesting idea. When astronomers observe distant objects, they are not seeing them exactly as they exist today. Instead, they are seeing them as they were when the light began its journey. Looking into space is also looking into the past. For nearby stars, the delay is only a few years. But for distant galaxies, the delay can be millions or even billions of years. In some cases, astronomers observe galaxies whose light began traveling toward Earth before our planet even existed. This time-based way of measuring space is one of the most fascinating aspects of astronomy. It means that every observation carries a piece of history with it. The concept of the light year allows scientists to describe these distances clearly. Instead of writing huge numbers in kilometers, they can simply say how many years light would need to travel between 2 points. This makes it easier to compare distances across the universe. A star 10 light-years away is twice as far as a star 5 light-years away. A galaxy 1 million light-years away is much farther still. Using light years allows astronomers to scale distances naturally as they move from nearby stars to entire galaxies. This system becomes especially important when studying the Milky Way. Our galaxy contains hundreds of billions of stars spread across an enormous region of space. The distances between these stars are so large that light years become the most practical way to measure them. Once we begin thinking about distance in terms of light travel time, we can start asking much larger questions. For example, how far away are different regions of our galaxy? How long does it take for light to travel between them? And how long would it take to cross the Milky Way itself? Before we can answer those questions, we need to take a closer look at one particular part of our galaxy, the mysterious region at its center. If we want to understand the size of the Milky Way, one helpful place to begin is the center of our galaxy. The Milky Way is not just a loose cloud of stars. It has a structure, with many of its stars arranged in a wide spiral disk that circles around a dense central region. This crowded middle area is known as the Galactic Center. From our position in space, the Galactic Center lies in the direction of the constellation Sagittarius. If you were able to travel there, you would find a region where stars are packed far more closely together than they are in our part of the galaxy. But the Galactic Center is very far away from Earth. Astronomers estimate that our solar system sits about 26,000 light-years from this central region. In other words, light traveling from the center of the Milky Way must journey across 26,000 years of space before reaching Earth. This idea can be surprising at first. When we observe the Galactic Center through telescopes, the light that reaches our eyes tonight actually began its journey long ago. The light left that region of space 26,000 years in the past and has been traveling toward us ever since. To understand what that means, it can help to compare that time span with human history. 26,000 years ago, humans had not yet built cities or written languages. Agriculture had not yet developed. Most human communities lived as small groups of hunter-gatherers, moving across landscapes in search of food. The pyramids of Egypt would not be built for another 20,000 years. Ancient civilizations such as Rome, Greece, and China still lay far in the future. Yet during all that time, the light from the center of our galaxy was already traveling toward Earth. Only now is that light finally arriving. This example helps illustrate the enormous scale of our galaxy. Even a single journey from the center of the Milky Way to our solar system takes tens of thousands of years for light to complete. And remember, light is the fastest thing known in the universe. Nothing can travel faster than light through empty space. Even the most advanced spacecraft humans have built travel vastly slower than this cosmic speed limit. For example, the fastest spacecraft ever launched from Earth move at speeds of only a few tens of kilometers per second. That may sound impressive, but compared to the speed of light, it is extremely slow. At those speeds, reaching the center of our galaxy would take far longer than 26,000 years. In fact, it would take many millions of years. This comparison helps show why astronomers rely on light itself when measuring cosmic distances. Light can cross the vast spaces between stars much faster than anything humans can currently build. But the Galactic Center is not just an empty region of space filled with stars. Astronomers have discovered that the very center of the Milky Way contains something even more extraordinary: a supermassive black hole. This black hole is known as Sagittarius, a star, often pronounced Sagittarius, a star. It contains millions of times the mass of our Sun and sits at the heart of the galaxy, surrounded by thousands of tightly packed stars. Scientists cannot see the black hole directly, but they can observe the motion of stars orbiting around it. By carefully tracking these stellar orbits, astronomers were able to determine the black hole's presence and measure its mass. Despite its enormous mass, Sagittarius A star does not control the entire galaxy by itself. Instead, the gravity of billions of stars and large amounts of unseen matter work together to hold the Milky Way together. Our solar system is simply one small part of this vast structure. We orbit the galaxy's center slowly, traveling along with billions of other stars in a long journey that takes hundreds of millions of years to complete. The distance between our solar system and the galactic center is just one small piece of the larger puzzle. Because the Milky Way extends both inward toward the center and outward toward distant regions of the disk, the total size of the galaxy must be much larger than this single measurement. Understanding how far we are from the center gives astronomers an important reference point. From that starting point, scientists can begin mapping the rest of the galaxy and estimating how far its spiral arms and outer regions stretch into space. And once we start looking beyond our own position in the Milky Way, the scale of the galaxy begins to grow far larger than most people imagine. Now that we know how far we are from the center of the Milky Way, we can begin to understand where our solar system fits inside the galaxy. The Milky Way is not shaped like a sphere. Instead, it is a spiral galaxy, meaning most of its stars are arranged in a wide, rotating disk, with curved arms that extend outward from the center. If you could somehow travel far outside the Milky Way and look back at it from a distance, you would likely see something similar to other spiral galaxies astronomers observe across the universe. The galaxy would appear as a glowing disk of stars, with graceful spiral arms winding outward from a bright central region. Our solar system is located somewhere within that disk, but we are not located in the middle of the galaxy. Instead, our Sun sits in a quieter region of one of the galaxy's spiral arms. This region is sometimes called the Orion Arm or the Orion Spur. The Orion Arm is not one of the largest spiral arms in the Milky Way. It is more like a smaller branch that sits between two much larger arms known as the Perseus Arm and the Sagittarius Arm. Within this branch of the galaxy lies our solar system, moving slowly through space along with many other nearby stars. When astronomers look at the Milky Way, they often describe our position as being about halfway between the Galactic Center and the outer edge of the galaxy. We are not deep inside the crowded central bulge where stars are packed closely together. We are also not near the very edge where stars become more sparse. Instead, we occupy a middle region of the galactic disk. This location is actually quite fortunate for life on Earth. The central region of the Milky Way contains far more stars than our local neighborhood. With so many stars packed closely together, there would likely be much stronger radiation and more gravitational disturbances. Stars passing close to each other could potentially disrupt planetary systems. Out here in the Orion Arm, the environment is calmer. Stars are spaced much farther apart, which means our solar system has remained relatively stable for billions of years. This stability may have played an important role in allowing life to develop on Earth. Even though the distances between stars are enormous, the Milky Way still contains an incredible number of them. Astronomers estimate that there may be between 100 billion and 400 billion stars in our galaxy. Many of these stars have their own planets, forming countless solar systems spread across the Milky Way. Our Sun is simply one star among these vast numbers. Yet despite being only one star in such a huge galaxy, our solar system is not standing still. Like all stars in the Milky Way, the Sun is orbiting the center of the galaxy. Gravity from the combined mass of the galaxy keeps stars moving along curved paths around the galactic center. Our solar system travels through the Milky Way at a speed of about 220 kilometers per second. That may sound incredibly fast, but the distance around the galaxy is so large that completing one full orbit takes a very long time. In fact, the Sun needs roughly 225 to 250 million years to make one complete journey around the galaxy. Astronomers sometimes call this a galactic year. To put that in perspective, the dinosaurs first appeared on Earth about 1 galactic year ago. Since that time, our solar system has completed roughly one full orbit around the Milky Way. During all of human history, our solar system has only traveled a tiny fraction of that long path around the galaxy. As the Sun moves along its orbit, it carries the entire solar system with it. Earth, along with the other planets, travels through space as part of this larger galactic journey. Even while we stand still on the ground, our planet is moving through the galaxy at incredible speed. Understanding where we are in the Milky Way helps give us a sense of perspective. We are not at the center of the galaxy. We are not in a special or central location. Instead, we occupy a small, ordinary region within one spiral arm of a vast stellar system. But even though our position may seem modest, it gives us an excellent vantage point for studying the rest of the galaxy. From here, astronomers can observe the stars around us and gradually map the larger structure of the Milky Way. And when scientists began studying these patterns of stars, they started to uncover the larger shape of the galaxy itself. If you wanted to learn the shape of a distant object in space, the easiest way would usually be to step back and take a picture of it. Astronomers do this all the time with other galaxies. Modern telescopes can capture beautiful images of spiral galaxies millions of light years away. In those pictures, the full structure of the galaxy is clearly visible. You can see the spiral arms, the bright center, and the outer edges of the disk all at once. But the Milky Way presents a special challenge. Unlike those distant galaxies, we are not observing the Milky Way from the outside. We are located inside it. Our solar system sits within the galaxy's disk, surrounded by billions of other stars. Because of this, we cannot simply move far enough away to photograph the entire galaxy from above. Instead, astronomers must study the Milky Way from within it, looking outward in every direction and slowly piecing together its structure. This situation can be compared to trying to map a forest while standing among the trees. If you walk through a dense forest, you can clearly see the trees around you. You may even see hundreds of them in every direction. But understanding the full shape of the forest, how wide it is, where it begins, and where it ends, is much harder. The trees themselves block your view, and the landscape stretches far beyond what you can easily observe from one location. Astronomers face a similar problem when studying the Milky Way. From Earth, we can observe nearby stars with great detail. We can also see distant stars scattered across the sky. But because we are inside the galaxy, our view is limited. We cannot see the entire structure at once. Early astronomers had an especially difficult time with this challenge. Before the invention of powerful telescopes, the night sky appeared mostly as a collection of individual stars. Some regions looked brighter than others, but the larger structure of the Milky Way remained mysterious. Scientists could only observe a small portion of the galaxy at a time. As telescopes improved, astronomers began to notice patterns. They realized that stars were not distributed evenly across the sky. Instead, they seemed to cluster along a wide band that stretched across the heavens. This band appeared brighter because it contained far more stars than other parts of the sky. But even with better instruments, much of the galaxy remained hidden. One of the biggest obstacles to observing the Milky Way is interstellar dust. This dust consists of tiny particles floating between the stars. Although these particles are extremely small, they can still block and scatter light traveling across space. when light from distant stars passes through thick clouds of dust, it can become dimmed or completely hidden from view. As a result, some parts of the galaxy are very difficult to observe using ordinary visible light. For many years, astronomers believed the Milky Way was smaller than it truly is, because these dust clouds prevented them from seeing distant regions of the galaxy. It was only later, when scientists developed new types of telescopes, that they began to overcome this problem. Infrared telescopes, for example, can detect longer wavelengths of light that pass more easily through dust clouds. Radio telescopes can also observe signals that travel through these dusty regions. By using these tools, astronomers were able to study parts of the Milky Way that had previously been hidden. Slowly, piece by piece, scientists began building a more complete map of our galaxy. They measured distances to nearby stars, tracked the movement of stellar clusters, and studied the distribution of gas and dust throughout the galaxy. Over time, these observations revealed that the Milky Way is a vast spiral system, with a central bulge and multiple curved arms extending outward. But long before astronomers understood these details, people had already noticed one of the galaxy's most recognizable features. Even without telescopes, the Milky Way reveals itself in a familiar and beautiful way. On very dark nights, far from city lights, a soft glowing band can be seen stretching across the sky. This glowing band is the combined light of billions of distant stars, and it provides our first visible clue about the true shape of the galaxy we live in. Long before telescopes were invented, people around the world noticed something unusual about the night sky. On the darkest nights, far away from bright city lights, a faint glowing band could be seen stretching across the heavens. This soft ribbon of light runs from one side of the sky to the other. It looks almost like a pale cloud, or a thin trail of mist drifting through the stars. Today we call this glowing band the Milky Way. For thousands of years, different cultures created stories to explain what they were seeing. In ancient Greece, the band of light was said to be milk spilled across the sky by the goddess Hera. In other cultures, it was described as a road, a river, or even a path followed by spirits. Although these stories were imaginative, they were all attempts to explain the same mysterious feature of the night sky. At first, people could only see this band with the naked eye. It appeared as a smooth glow without clear details. But when telescopes were invented in the early 1600s, astronomers began to look more closely. One of the first people to do this was Galileo Galilei. When Galileo pointed his telescope toward the Milky Way, he discovered something remarkable. The pale glow was not a cloud at all. Instead, it was made of an enormous number of stars, packed so closely together that they blended into a single band of light. What appeared to be a mist was actually the combined glow of countless distant suns. This discovery helped scientists realize that the Milky Way was not simply a decorative feature of the night sky. It was a vast system of stars that our own sun was part of. But why does the Milky Way appear as a band instead of filling the entire sky evenly? The answer has to do with the shape of our galaxy. As astronomers later discovered, the Milky Way is shaped like a wide, flattened disk. Most of the galaxy's stars lie within this disk, orbiting around the Galactic Center. Because the disk is relatively thin compared to its width, the stars are concentrated along a flat plane. Our solar system sits inside this disk. When we look up into the night sky, we are looking outward in every direction from within the galaxy. If we look above or below the disk, we see relatively fewer stars, because there are not as many stars in those directions. But when we look along the plane of the disk, our line of sight passes through huge numbers of stars. Imagine standing inside a long hallway filled with lights. If you look straight down the hallway, you can see many lights stretching into the distance. But if you turn and look at the wall beside you, you will only see a few lights nearby. Something similar happens when we observe the Milky Way. When we look along the disk of the galaxy, our view passes through billions of stars. Their combined light creates the glowing band that stretches across the sky. This band marks the direction where the galaxy's disk lies. The brightness of the band also changes depending on where you look. Some sections appear brighter and thicker than others. These brighter regions often point toward areas where stars are more densely packed, especially toward the center of the galaxy. Other regions appear darker. These dark patches are often caused by large clouds of interstellar dust, blocking the light from stars behind them. Even today, the Milky Way remains one of the most beautiful sights visible from Earth. On a clear night in a dark location, the band of light can be seen arching across the entire sky. For many people, seeing the Milky Way for the first time can be surprising. Modern cities are often so bright that this feature of the sky becomes invisible. Only when the sky is truly dark does the full glow of the galaxy become visible. This simple observation, just looking at the sky, already tells us something important about the structure of the Milky Way. The fact that the stars form a band instead of spreading evenly across the sky suggests that they are arranged in a flat system rather than a sphere. In other words, the night sky itself contains clues about the shape of the galaxy we live in. As astronomers continued studying the stars along this glowing band, they began noticing patterns in how the stars were arranged. These patterns eventually revealed that the Milky Way is not just a flat disk of stars. It also contains large curved structures known as spiral arms. And these spiral arms form the next important piece of the Milky Way structure. When astronomers first realized that the Milky Way was a flattened system of stars, they still did not fully understand what that system looked like. From Earth, we are stuck inside the galaxy. That means we cannot simply step outside and take a photograph of it from above. Instead, scientists had to slowly piece together its structure using careful observations. Over time, a clearer picture began to emerge. The Milky Way is not just a smooth disk filled evenly with stars. Instead, many of those stars are arranged into large curved patterns that wind outward from the center of the galaxy. These patterns are known as spiral arms. If you could view the Milky Way from far above, it would look something like a giant cosmic pinwheel. Several enormous arms would be seen spiraling outward from a bright central region, each filled with stars, gas, and dust. These arms are some of the most important structures in our galaxy. One reason they stand out so clearly is that spiral arms are regions where new stars are constantly forming. Inside the galaxy are vast clouds of gas and dust, known as molecular clouds. these clouds can collapse under their own gravity, forming new stars. Spiral arms tend to contain many of these clouds, making them active regions of starbirth. Because many young stars are extremely bright, spiral arms often shine more strongly than other parts of the galaxy. Young stars are typically larger, hotter, and more luminous than older stars. Their light helps highlight the curved shapes of the spiral arms when astronomers observe distant galaxies. But something interesting happens when scientists study how spiral arms behave. The stars inside them are not permanently attached to the arms themselves. Instead, stars slowly move in and out of spiral arms as they orbit the galaxy. To understand this, it helps to imagine a traffic jam on a busy highway. In a traffic jam, the slowdown itself can move along the road, even though individual cars are constantly entering and leaving the crowded area. The traffic jam is more like a pattern than a permanent group of specific cars. Spiral arms behave in a similar way. They are often described as density waves moving through the disk of the galaxy. As gas and stars travel through these regions of higher density, the gas can compress and trigger the formation of new stars. Once those stars form, they continue orbiting the galaxy, gradually drifting away from the spiral arm where they were born. This means the spiral arms are constantly being refreshed with new stars. The Milky Way is believed to contain several major spiral arms. Among the most well-known are the Perseus Arm, the Sagittarius Arm, the Centaurus Arm, and the Norma Arm. There are also smaller structures between these major arms called spurs or minor arms. Our solar system happens to sit within one of these smaller structures. The region we live in is called the Orion Arm, sometimes referred to as the Orion Spur. It lies between the larger Sagittarius and Perseus spiral arms. Although it is smaller than the main arms, it still contains many stars, nebulae, and stellar clusters. From our location inside the Orion Arm, the spiral structure of the Milky Way is difficult to see directly. Large clouds of dust block our view across much of the galaxy, especially toward the center. Because visible light cannot easily pass through these dense dust clouds, astronomers have had to rely on other methods to map the galaxy's structure. Radio waves and infrared light can travel through dust much more easily than visible light. Using radio telescopes and infrared observatories, scientists have been able to trace the locations of gas clouds and star-forming regions across the galaxy. By mapping these regions, they gradually revealed the shape of the Milky Way's spiral arms. Today, astronomers believe the Milky Way contains 4 major spiral arms, along with several smaller branches and spurs. Each of these arms stretches tens of thousands of light years across the galaxy. The spiral structure also plays an important role in shaping the environments where stars and planets form. Many of the most active star-forming regions in the galaxy are found along these curved arms. Massive nebulae, glowing clusters of newborn stars, and powerful stellar winds all contribute to the constantly changing landscape of the spiral arms. Although our solar system is currently located in a quieter region of the Orion Arm, it still shares the galaxy with these vast star-forming structures. Every star we see in the night sky, including our Sun, is part of this enormous rotating spiral system. And while the spiral arms define much of the Milky Way's visible structure, they are only one part of the galaxy. At the very center of the Milky Way lies a region far denser, brighter, and more mysterious than anything found in the spiral arms. If you follow the glowing band of the Milky Way across the night sky, one region appears brighter and thicker than the rest. This area lies in the direction of the constellation Sagittarius, and it marks the direction of the center of our galaxy. The Galactic Center is one of the most fascinating and mysterious places in the Milky Way. It is located about 26,000 light-years away from Earth, deep within the crowded heart of the galaxy. From our perspective, it is hidden behind enormous clouds of dust and gas. These clouds block most visible light, which is why the Galactic Center does not appear as a brilliant point in the sky, despite containing a huge concentration of stars. For centuries, astronomers could not see what was actually there. Only in the 20th century did scientists begin using radio waves, infrared light, and X-rays to study the region beyond the dust. These forms of light can travel through the dense clouds that obscure the center in visible wavelengths. As these observations improved, astronomers discovered that the center of the Milky Way is an incredibly crowded environment. The region contains millions of stars packed into a relatively small volume of space. Star clusters sit close together, and powerful bursts of energy emerge from gas clouds that are constantly being heated and compressed. Compared with our quiet location in the Orion Arm, the Galactic Center is a far more extreme place. One of the most remarkable discoveries about the Galactic Center came from careful measurements of how stars move in this region. Astronomers noticed that many stars orbit around an invisible point in space at extremely high speeds. Some stars complete their orbits in just a few years, traveling at thousands of kilometers per second. Such rapid motion suggested that an enormous amount of mass must be concentrated at the very center. But the strange part was that no ordinary cluster of stars could account for the gravitational pull required to produce those speeds. The best explanation was something far more unusual. At the center of the Milky Way sits a supermassive black hole. This object is known as Sagittarius A star, pronounced Sagittarius A star. It contains roughly 4 million times the mass of our Sun, compressed into a region far smaller than our solar system. A black hole forms when matter becomes so densely packed that its gravity prevents even light from escaping. Once something crosses the boundary around a black hole, called the event horizon, it cannot return. Although black holes themselves emit no light, astronomers can detect them indirectly by studying how nearby stars and gas behave. The stars orbiting Sagittarius A star follow paths that reveal the presence of a massive, invisible object at the center of their motion. These observations provide some of the strongest evidence that the Milky Way contains a supermassive black hole. Despite its enormous mass, Sagittarius A star does not currently consume large amounts of material. In some galaxies, supermassive black holes are extremely active. They pull in large quantities of gas and dust, which heat up and release intense radiation as they spiral inward. These active galactic centers can outshine the entire galaxy around them. The Milky Way's black hole, however, is relatively quiet. Most of the time it sits in a low activity state, occasionally swallowing small amounts of gas that drift too close. When this happens, brief bursts of energy can be detected in X-rays or radio waves. Even though the black hole dominates the gravitational center of the galaxy, its influence fades quickly with distance. At the scale of the entire Milky Way, the motion of stars is determined mainly by the combined gravity of hundreds of billions of stars, along with vast quantities of gas, dust, and dark matter. Our solar system, for example, orbits the center of the galaxy far beyond the region where the black hole's gravity directly dominates. In fact, the Sun takes about 225 to 250 million years to complete one full orbit around the galactic center. This enormous journey is sometimes called a galactic year. During that time, the Sun and its planets travel through different regions of the Milky Way's spiral structure. Although the galactic center is far away and hidden from direct view, it still plays a crucial role in shaping the overall structure of the galaxy. The immense mass at the center helps anchor the rotating disk of stars that extends tens of thousands of light years outward. But even the galactic center is not the full story of the Milky Way. Beyond the spiral arms and far outside the bright disk of stars lies a much larger and more mysterious component of the galaxy, one that extends far beyond what we can easily see. This outer region forms a vast spherical envelope surrounding the Milky Way. When most people imagine the Milky Way, they picture the bright spiral disk filled with stars and glowing clouds of gas. This disk, along with its spiral arms, is certainly the most visible part of our galaxy. But the Milky Way does not end at the edge of its spiral arms. Far beyond the thin disk lies a much larger and more diffuse region known as the Galactic Halo. The halo forms a vast spherical envelope surrounding the entire galaxy. While the disk stretches roughly 100,000 light-years across, the halo extends far beyond that, reaching perhaps several 100,000 light-years into space. Compared to the crowded spiral arms, the halo is extremely sparse. Stars in the halo are spread very far apart, and the region contains far less gas and dust than the disk. Because of this, the halo is much harder to observe. It does not glow brightly like the Milky Way band we see in the night sky. Yet it still plays an important role in the structure of the galaxy. One of the most noticeable features of the halo is the presence of globular clusters. Globular clusters are dense spherical groups of stars that orbit the galaxy far above and below the galactic disk. Each cluster can contain hundreds of thousands or even millions of stars tightly bound together by gravity. These clusters are among the oldest objects in the Milky Way. Many globular cluster stars formed more than 12 billion years ago, not long after the galaxy itself began to take shape. Because of their great age, studying these clusters helps astronomers learn about the early history of the Milky Way. Unlike stars in the disk, which move in relatively flat circular paths around the galactic center, globular clusters follow much more varied orbits. Some plunge through the galactic disk before rising far above it again. Others travel along wide, elongated paths that carry them deep into the halo. Their movements reveal that the halo is not organized like the rotating disk of the galaxy. Instead, objects in the halo move in many different directions, creating a much more chaotic structure. Another interesting difference between halo stars and disk stars involves their chemical composition. Stars in the galactic disk often contain heavier elements such as carbon, oxygen, silicon, and iron. These elements are created inside stars and spread into space when stars die in supernova explosions. Over billions of years, new generations of stars formed from this enriched material, gradually increasing the abundance of heavy elements in the galaxy. Halo stars, however, often contain far fewer heavy elements. This suggests that they formed very early in the galaxy's history, before many cycles of star formation had taken place. In a sense, halo stars act as ancient fossils from the early universe. Beyond the visible stars and globular clusters, the halo contains something even more mysterious. Astronomers have discovered that galaxies, including the Milky Way, are surrounded by enormous quantities of dark matter. Dark matter does not emit light, reflect light, or absorb light in ways that telescopes can detect. Yet its gravitational effects can be measured by observing how stars and gas move within galaxies. When scientists studied the rotation of galaxies, they found something surprising. Stars far from the center were orbiting much faster than expected. Based only on the visible matter in galaxies, these outer stars should move more slowly. Instead, their speed suggested that a huge amount of unseen mass must be present. This unseen mass appears to form a massive dark matter halo surrounding the visible galaxy. In the Milky Way, the dark matter halo likely contains several times more mass than all the stars combined. Although we cannot see dark matter directly, its gravity helps hold the galaxy together. Without it, the outer stars would not remain bound to the galaxy in the way we observe. The presence of dark matter also affects how galaxies form and evolve over cosmic time. Computer simulations suggest that galaxies like the Milky Way began forming within large clouds of dark matter. As gas cooled and collapsed within these dark matter halos, stars gradually formed, eventually creating the visible galaxy we see today. So while the spiral disk may be the most recognizable part of the Milky Way, it represents only a fraction of the galaxy's full structure. The halo extends far beyond the bright stars, containing ancient clusters, scattered stars, and an enormous invisible framework of dark matter. Together, these components create a galaxy far larger and more complex than what we see in the night sky. And even within this vast system, our solar system occupies only a tiny and quiet corner of the galaxy's immense structure. With hundreds of billions of stars spread across a galaxy, more than 100,000 light-years wide, it can be difficult to picture exactly where we are within the Milky Way. The truth is that our solar system does not sit anywhere near the center of the galaxy. Instead, we live in a relatively quiet outer region of the galactic disk. Our position is about 26,000 light-years from the Galactic Center, placing us roughly halfway between the center of the Milky Way and its outer edge. This location turns out to be surprisingly comfortable. The center of the galaxy is a much more crowded and energetic place. Stars there are packed much closer together, and intense radiation from energetic events can make the environment far more chaotic. Our region, by contrast, is relatively calm. The Sun lies within a smaller structure known as the Orion Arm, sometimes called the Orion Spur. This is not one of the Milky Way's major spiral arms, but rather a smaller branch located between two larger arms, the Sagittarius Arm, and the Perseus Arm. Although it is considered a minor structure, the Orion Arm still contains thousands of stars and many star-forming nebulae. Some of the most familiar stars in the night sky are actually located within this same region of the galaxy. Bright stars like Betelgeuse, Rigel, and many others belong to nearby stellar neighborhoods within the Orion Arm. From our position inside the disk, the stars around us appear scattered across the sky in every direction. But when astronomers measure the distances and motions of these stars, they find that they are all part of the same enormous rotating system. The Sun itself is not stationary within the Milky Way. It is constantly moving as it orbits the galaxy's center. In fact, our solar system travels at a speed of roughly 220 kilometers per second as it moves along its galactic orbit. At that speed, it still takes an incredibly long time to complete a single trip around the galaxy. One full orbit of the Sun around the Milky Way is called a galactic year, and it lasts about 225 to 250 million Earth years. This means that during the entire history of Earth, the Sun has completed only about 20 galactic orbits. When the dinosaurs first appeared on Earth, the solar system was located in a completely different part of the galaxy than it is today. While the Sun moves along this enormous path, it also drifts slightly above and below the galactic plane. The Milky Way's disk is not perfectly flat. Instead, stars oscillate gently up and down as they orbit the center. The Sun currently sits close to the middle of this disk, but over time, it slowly moves above and below it in a gradual wave-like motion. Each vertical oscillation takes tens of millions of years. Despite this constant motion, the distances between nearby stars remain enormous. Even the closest star system to us, Alpha Centauri, lies more than 4 light-years away. In most regions of the galaxy, stars are separated by similarly vast distances. This means that collisions between stars are extremely rare, even though the galaxy contains so many of them. Our position in the Milky Way also influences what we can see in the night sky. Because we are located within the galactic disk, our view across the galaxy is partially blocked by clouds of gas and dust. These interstellar clouds absorb and scatter visible light, hiding many distant stars from direct observation. This is one reason why mapping the full structure of the Milky Way has been such a difficult challenge for astronomers. In contrast, if we lived far above the disk of the galaxy, we would have a much clearer view of the Milky Way's spiral structure from the outside. From our current vantage point, however, we must study the galaxy from within, gradually building a picture of its structure using measurements of star distances, radio signals from gas clouds, and observations in infrared light. Even with these limitations, astronomers have been able to determine that the Milky Way is a vast rotating system with a complex structure of spiral arms, star clusters, and interstellar clouds. And within this enormous galaxy, our solar system occupies only a tiny region along one of its smaller spiral branches. But even though our location might seem ordinary, it places us in a stable environment where stars are widely spaced and catastrophic events are relatively rare. This quiet corner of the Milky Way may have played an important role in allowing life to develop on Earth, And as we continue exploring the galaxy, we are gradually discovering that the Milky Way is not alone in the universe. It is part of a much larger cosmic neighborhood filled with other galaxies. For most of human history, people had no way of knowing how large the Milky Way actually was. The glowing band in the night sky was visible to anyone who looked up on a dark night, but its true nature remained mysterious for thousands of years. Without telescopes or modern instruments, the Milky Way appeared simply as a faint river of light crossing the heavens. Many early thinkers assumed that this band of light contained all the stars that existed. In fact, some early astronomers believed the Milky Way might represent the entire universe. If every visible star belonged to this single structure, then perhaps the universe itself was simply a large collection of stars surrounding Earth. This idea persisted for a long time because measuring distances to stars was incredibly difficult. Even the closest stars are so far away that their distances cannot be measured in ordinary units, like kilometers or miles. Instead, astronomers eventually had to develop new methods that could estimate distances across the vast emptiness of space. The first important clues came in the late 19th and early 20th centuries, when telescopes became powerful enough to reveal far more stars than the naked eye could see. Through these improved telescopes, astronomers discovered that the Milky Way was filled with enormous numbers of faint stars that were invisible without magnification. This discovery suggested that the galaxy might be much larger than anyone had previously imagined. At the same time, scientists began developing ways to measure how far away some of these stars might be. The challenge was enormous. When we look at the night sky, stars appear scattered across a flat dome above us. Without additional information, it is almost impossible to tell which stars are nearby and which ones lie far deeper in space. Two stars may appear side by side in the sky, even though one is hundreds of times farther away than the other. Early astronomers therefore needed a way to determine the true three-dimensional structure of the Milky Way. During the early 1900s, researchers began collecting large amounts of observational data. They carefully measured the brightness of stars, recorded their positions in the sky, and compared observations made from different observatories around the world. Slowly, astronomers started assembling the first crude maps of star locations. These early maps did not yet reveal the spiral shape of the Milky Way, but they provided an important first step toward understanding its structure. One of the scientists who contributed significantly to these efforts was Jacobus Kapteyn, a Dutch astronomer who attempted to map the distribution of stars throughout the galaxy. Kapteyn analyzed the brightness and motion of thousands of stars, hoping to estimate their distances and positions. Using this data, he constructed one of the earliest models of the Milky Way. His model suggested that the galaxy was shaped somewhat like a flattened disk, with the sun located near the center. Although we now know this part of the model was incorrect, the effort itself was a remarkable achievement for its time. Kapteyn and other astronomers were working with limited tools and incomplete data, yet they were beginning to uncover the true scale of the galaxy. The main difficulty was that interstellar dust blocked much of the light coming from distant stars. This dust made distant regions of the galaxy appear dimmer than they really were. causing early measurements to underestimate how far the Milky Way extended. Even with these limitations, the growing number of star measurements hinted that the galaxy was far larger than previously believed. Astronomers realized that if they could find reliable ways to measure star distances, they could begin constructing a far more accurate map of the Milky Way. That challenge soon led to the development of several powerful distance measuring techniques. The first of these techniques relied on a subtle shift in how nearby stars appear when viewed from different points in Earth's orbit. This method became one of the earliest reliable tools for measuring the distances to stars close to our solar system. It is known as stellar parallax. One of the first reliable ways astronomers learned to measure distances in space is a method called parallax. The idea behind parallax is surprisingly simple. It relies on the fact that an object can appear to shift slightly when viewed from two different positions. You may have noticed this effect in everyday life. If you hold your finger out in front of your face and look at it with one eye closed, then switch to the other eye, your finger seems to move slightly against the background. Your finger is not actually moving. The shift happens because each eye views the finger from a slightly different angle. Astronomers realized that a similar effect could be used to measure distances to nearby stars. Instead of using two eyes, however, they used two different positions of Earth in its orbit around the Sun. As Earth travels around the Sun once each year, our viewing position in space changes by about 300 million kilometers. 6 months after observing a star from one side of Earth's orbit, we are viewing it again from the opposite side. This shift provides two different viewing angles of the same star. If the star is relatively close to us, it will appear to move slightly against the background of much more distant stars. This tiny apparent motion is called stellar parallax. The amount of this shift is extremely small. Even the nearest stars move only a tiny fraction of a degree across the sky when measured using parallax. In fact, the shifts are usually measured in units called arcseconds, which divide a single degree into 3,600 smaller parts. For most stars, the shift is far smaller than 1 arcsecond. Because these angles are so tiny, measuring them accurately requires extremely precise instruments. The first successful measurement of stellar parallax was made in 1838 by Friedrich Bessel, a German astronomer. Bessel studied the star 61 Cygni, which was known to move relatively quickly across the sky. After carefully observing the star over time, Bessel detected a small parallax shift that revealed its distance from Earth. This measurement confirmed something important. Stars were not just distant lights fixed to the sky. They were incredibly far-away objects scattered through space. Using parallax measurements, astronomers could now determine distances to nearby stars with much greater confidence. To make these measurements easier to work with, scientists created a special unit of distance called the parsec. A parsec is defined as the distance at which a star would show a parallax shift of exactly 1 arcsecond as Earth moves around the Sun. 1 parsec equals about 3.26 light years. Although this unit might sound unusual, it allows astronomers to calculate distances directly from parallax measurements using simple geometry. As telescopes improved, astronomers measured the parallax of more and more nearby stars. This allowed them to build the first accurate maps of the solar neighborhood, showing the positions of stars located within a few dozen light-years of the Sun. These early measurements revealed that space is far emptier than people once imagined. Even the closest stars are separated by enormous distances. For example, the nearest star system beyond our own, Alpha Centauri, lies about 4.37 light-years away. In other words, light from that system takes more than 4 years to reach Earth. While parallax is extremely useful, it has an important limitation. Because the shifts are so tiny, the method only works well for stars that are relatively close to Earth. For stars located farther away, the parallax angle becomes too small to measure accurately. For many years, parallax measurements could only reach distances of a few hundred light-years,